let's talk about expression for elevation of boiling point. Now, when we are doing the graph, the solution 1, elevation of boiling point for solution 1. Elevation of boiling point for solution 1, that is delta TB1, that is equal to T1 minus TB. That was for the solution 1. Similarly, for solution 2, we have delta TB2, that will be is equal to T2 minus TB. All right. Now, with the help of the graph only, we have a relationship. Directly, we have to do it. Delta TB1 delta TB1 upon delta TB2 that have delta P1 upon delta P2. Now here, if you want, you can write it out delta P1. What it will be the delta P1 here? What will be the delta P1?
P naught minus P1.
For P naught minus P1. P naught also, you know, vapor pressure for the pure solvent. P1 also, you know, that is the vapor pressure for solution 1. Similarly, we have delta P2, and the delta P2, what we have, P naught minus P2. So that is P naught is a vapor pressure of a pure solvent, and P2 is a vapor pressure of solution 2, which we have seen in the graph. So we have a direct relationship with the elevation change in boiling point and with respect to vapor pressure. From here, delta T1 upon delta TB2, delta P1 upon delta P2, we got a relation. Now, delta P1 is an elevation of boiling point for solution 1. This is an elevation of boiling point for solution 2. Delta P1. Delta P1, we have vapor pressure for solution 1. And delta P2, we have a vapor pressure for solution 2. And how we got delta P1, delta P2? We have P naught minus P1 and P naught minus P2. All these are the same thing we have discussed in the graph. P naught, vapor pressure of pure solvent. P1 for solution 1. P2 for solution 2. All right. Now, this follows a relationship, that is a direct relationship we have, because delta TP1 is equal to delta P1. It means elevation and change in elevation of boiling point is directly proportional to change in vapor pressure. We can conclude from here delta TB is directly proportional to The elevation of boiling point is directly proportional to what? Lowering of vapor pressure. All right. So this relation you will remember, and we that will help you. They ask you a simple question regarding this also. They have given the four options in the multiple choice. So delta TB is directly proportional to the, that is, elevation of boiling point is directly proportional to the lowering of vapor pressure. All right. Now, lowering of vapor pressure, when we talk about the lowering of vapor pressure, then we have studied the Raoult's law. And Raoult's law, according to Raoult's law, P naught minus P upon P naught, that is equal to mole fraction of solute. Yes or no? Now we have another relationship. Remember this equation. Delta TB is directly proportional to delta P. Now, according to Raoult's law, we are doing this equation we have used for so many numericals. P naught that can be is equal to number of moles of solute upon number of moles of solvent. That can be equal to weight of solute upon its molecular mass upon weight, capital W, weight of solvent upon its molecular mass. It means P naught minus P upon T naught, that can be written as W upon, this will come down, M dash into M upon W. All these have the same symbol we have discussed. P naught minus P upon P naught. That is what we call it out as P naught minus P. We have delta P upon P naught. This we can write all right. So if we cross multiply this, so what we have, delta P is equal to P naught into M dash into W. Now what is here P naught here? That is the vapor pressure of a pure solvent. And what is M here? Yes, anyone?
That M is molar molar weight of this solvent.
Molar mass of solvent.
Solvent.
Right?
Solvent.
Yes. Solvent. This is a vapor pressure of a solvent. This is a molar mass of a solvent. We talk about the pure solvent. तो किसी भी pure solvent, this P naught value, say for water, it is fixed. Water 18. So these two are the constants for a pure solvent. The molar mass and P naught, vapor pressure of a pure solvent, these two are constant for a pure solvent. So when we are replacing this constant for a pure solvent, means P naught and M, that is molar mass, and P naught vapor pressure of solvent. If both are constant, then the formula will become delta P is equal to W upon M dash into W. This you got it. All right. And we got the relationship earlier, that is the delta TB is directly proportional to delta P. Change in elevation, that is boiling point, is the change in vapor, lowering of vapor pressure. Now, using that equation, we can have, instead of delta P, we can also write it here, delta TB M dash into W. Got it? So delta TB W upon M dash W. Now, this much clear? Means delta P or delta TB, they have a direct relationship from here. Now, yesterday I have told you about the molality. Molality is what? The formula I have given you. Number of moles of solute upon mass of solvent in kg. So what relationship we have this for small w with molality? That is what? Hurry fast. Tell me. I've given you that question also for solving the numerical. If you remember that 2.53, I think. So what we have the molality and W relationship.
W equals to M into M dash upon thousand and into capital W. That is given rate of solvent.
All right. It means if W is a mass of solvent in kg, it means that can be replaced by the whole this value with molality. This concept is very you have to remember this concept, that will help you to solve the numerical in terms of molality. Delta TB will be directly proportional to molality. And if we are replacing this constant delta TB, that will be delta TB proportionally constant Kb into M. This Kb is a constant which we talk about as molar elevation constant. This is known as molar elevation constant or ebullioscopic constant, delta Kb. Sorry, Kb. Delta Tb is equal to Kb into molality. So this expression is very important. this expression, so you have solved so many questions with respect to this. But when we talk about directly, now you have to face this equation for solving the numericals and this one. Delta TB is equal to Kb into molality, where Kb is the molar elevation or ebullioscopic constant. How you define this? Where say when the molality is equal to 1 or unity, then the elevation of change in elevation of boiling point is equal to molar elevation. If we say m is equal to 1, means the molality solution is equal to 1, then what will happen? Delta TB will be is equal to Kb. And Kb unit, you can derive it from here. Kb is equal to delta TB change in temperature upon molality. So delta TB unit will be what? Hurry fast. Delta TB, what we write it here? Kelvin, centigrade, molality, what we write it here?
Mole kg inverse.
Mole per kg.
Kg inverse, molar inverse. All right. So Kelvin molar inverse, we have degree centigrade molar inverse. They ask for the this unit, so you can write it the unit. Find it out with the help of formula. What is kb? To kb is the molar elevation or the ebullioscopic constant, and how you will define it. So they have given the two definition, that is elevation of boiling point is equal to the molar elevation, that is ebullioscopic constant, when the molality of the solution is unity. One, either you can write that they have given molar elevation constant is defined as equal to the elevation of boiling point when the molality of the solution is unity, means 1. We have seen here m is equal to 1, so delta TB is equal to Kb. Either from the equation you can write the definition there, and one more definition they have given is molar elevation constant is the elevation of boiling point, means the elevation, the increase in the boiling point on dissolving 1 mole of a substance in 1000 gram or 1 kg of the solvent. Either whether you will say that molality of a solution is unity or you define a molality there. They have in the second definition, they have defined the molality. That is the number of moles of solute dissolved in 1 kg of the solvent. All right. Now, and here delta TB is directly proportional. This equation I'm talking about. Delta TB is directly proportional to molality is very important in terms of showing that elevation of boiling point is the colligative property. If anyone asks you, just like the relative lowering of vapor pressure, mole fraction of the solute was there, and the mole fraction of the solute was what? Number of moles of solute. Number of moles of solute dissolved in a number of moles of solvent. So that was relative lowering of vapor pressure was the colligative property. If you want to prove why elevation of boiling point is a colligative property, how you will prove? Yes, anyone?
Actually, we write the expression
Answer is
delta
written
TB
on the white.
directly proportional to
Yes,
molality.
delta T. Yes, delta TB is directly proportional to molality. Elevation of boiling point is directly proportional to molality, which infers, which says, which discuss that molality of the solution is the number of moles of solute dissolvent per kg of the solvent. So what we talk about here, the number of moles Qualitative properties are those properties which depend upon the number of moles, which depend upon the number of solute, but does not depend upon the chemical nature. So no chemical nature are involved here. It involved only what? The number of solute particles. Clear? If anyone can ask why elevation of boiling point is a qualitative property, so you can have this derivation, that is delta TB is directly proportional to molality, which infers that molality of a solution is the number of moles of solute dissolved per kg of a solvent. It means number of solute particles are responsible, but not the chemical nature. Second important thing regarding the elevation of boiling point, we have equimolar solution of a solvent. Any non-volatile solute, you add it, or non-electrolyte solute you add it. They all have the same elevation of boiling point. When we have equimolar solution and we are adding non-volatile solute, non-electrolyte solute, no problem. They all have the same elevation. So these 2 points you have to remember. The equimolar solution of different non-volatile substance dissolved in the same solvent means the solvent has same, then they all have same elevation of boiling point. All right.